Good morning, students. Myself, Vijay Shankar from Electronics and Communication Engineering Department, Chevrolet Engineering College. Today, we are going to discuss about the properties of Fourier transform. In the last class, we already discussed about the properties of Fourier transform. That is linearity property, time shift property, frequency shift property, and time scaling property, frequency differentiation property, and time differentiation property, and convolution also. Now we go for integration property of the Fourier transformation. Integration property of Fourier transform. So what is the statement of integration property of the Fourier transformation? If x of t is a Fourier transform x of omega, then see somewhat different here. Integral minus infinite to t. Integral minus infinite to t x of tau d tau is a Fourier transformation pair of 1 by j omega into x of omega. 1 by j omega into x of omega. Following my dear students, you see in the time differentiation, you can observe here in the time differentiation, we are applying the differentiator to the time signal. We are applying here the differentiation to the time signal. See, the differentiation means whenever you are applying the differentiation for the time domain signal, j omega is multiplied with the frequency domain function of x of t, nothing but x of omega. When the integration, you see any variable we can take the integration. Let us see. Suppose if I am taking the t is a variable. 2t, let us take 2t is a variable. Following my dear students, 2t is a variable, and what is the derivation of this one? 2 is the derivation. Means coefficient of the t. And what is the integration of this one? T power t square by 2. T square by 2. Means the j omega is multiplied here and the j omega is divided by, so the t square you can take 2 into t. Otherwise the t square, the integral is t cube by the 3 integrations. Following my dear students. Now, when the time differentiation can apply the derivative to the time domain function, j omega is multiplied to the x of omega. Coming to the integration is also applying for the time domain only. Time domain, that j omega will get in the denominator, x of omega by j omega. X of omega by j omega. But here the integration is with respect to the d tau. Tau and the t is both are the variables only. I'm taking here the tau as one variable, but the limitations is from the minus infinite to the t. Not it is an infinite. Minus infinite to infinite, actually it is a minus infinite to up to the value of the t only. The integration of the time domain function, the Fourier transformation will get as 1 by j omega into x of omega. Okay, The integration in time represents smoothing in time domain. This smoothing in time corresponds to de-emphasizing the high frequency components of the signal. And to go for how we can prove this integration property of the Fourier transformation. Let x of t be expressed as, see my dear students here, x of t is equal to x of tau. Okay, I'm taking the t and the tau is both are the equal here. When now the x of t is equal to, in the left hand side, they're asking that the x of tau with respect to the d tau. So I'm integrating the minus infinite to t x of tau d tau, and the whole equation is I'm applying the derivative with respect to the dt. So derivative of integral, again it is a x of tau only. Derivative of the integral means whatever the function is there, the signal x of tau. X of t is equal to x of tau only. Derivative and the integral I am taking. Apply the Fourier transformation on both sides. F of t, not the f of t, f of x of t, nothing but the Fourier transform of x of t is equal to Fourier transformation of d by dt integral minus infinite to the t x of tau d tau. Okay. Only thing you have to remember here, the t and the tau is both are equal. I'm taking a left hand side is x of t signal and the right hand side is x of tau signal. Both the t and the tau is both are variables, and the statement saying that the integral minus infinite to infinite x of tau the d tau. So applying the integral and also to get it is a x of t, both are equal, can apply the derivative, because the tau with respect to the tau and with respect to the t both are equal, you get the same thing x of tau. Applying the Fourier transformation on both sides is equal to Fourier transform of the derivative function. What is the Fourier transformation of the derivative function? d by dt of x of t. You know the Fourier transformation is j omega into x of omega. The derivative of the time domain signal, the frequency domain signal is multiplied with the j omega. Here also you can see it is a Fourier transformation of the time domain signal only, the total time domain signal. The derivative of Fourier transformation of the derivative of this signal, the integral total signal. What will get the Fourier transformation of the derivative j omega into the Fourier transformation of actually the j omega x of omega you can also written as j omega into what is x of omega, nothing but the Fourier transformation of x of t. Fourier transformation of x of t, because if x of t the Fourier transformation x of omega. X of omega can also written as the Fourier transformation of x of t. Now the derivative of this x of t signal j omega into the Fourier transform of integral minus infinite to infinite x of tau d tau. Total signal is considered as x of t. Fourier transformation of d by dt of x of t. Nothing but j omega into the Fourier transformation of the signal. What is the Fourier transformation of x of t? X of omega. X of omega in the left hand side. Now see here, rewrite the expression by cross multiplying the Fourier transform of the integral minus infinite to the t x of tau d tau is equal to, after cross multiplying, 1 by j omega into x of omega. It is a Fourier transformation is equal to. But they are asking it is a Fourier transformation pairs. So remove here the Fourier transformation. You can write it as integral minus infinite to infinite x, not the infinite, it is a t, my dear students, x of tau d tau is a Fourier transformation pair with 1 by j omega into x of omega. Following, it is a Fourier transformation of x of t is equal to 1 by j omega into x of omega. What is that x of t here? The integral of the x of tau d tau. The integral minus infinite to t x of tau d tau is a Fourier transformation pair with 1 by j omega into x of omega. Following, a little bit confusion here. Only take it as a x of t is equal to x of tau, and x of t is equal to get it is a x of tau. One time you can apply the integral and with respect to the derivative also, dt and the d tau. Both are get cancelled, again it is x of tau. And apply the Fourier transformation on both sides. We already know the Fourier transformation of derivative of any signal. Here the signal is there. Derivative of this signal is a j omega into Fourier transformation of that signal. Understood? Fourier transformation of x of t, nothing but x of omega. You write as x of omega is equal to j omega. Fourier transformation of integral minus infinite to the t x of tau d tau. Cross multiply 1 by j omega into x of omega and remove this equal to, write as a pairs. Integral minus infinite to t x of tau d tau is a Fourier transformation pair 1 by j omega into x of omega. Understood? So to the times you can practice this one, definitely it is easy, will get to derive or the integration property of the Fourier transformation. Understood, my students? Then we go for the next property, modulation property. Modulation property. The statement of the modulation property saying that if x of t is a Fourier transformation of x of omega and y of t is a Fourier transformation of y of omega, then z of t is equal to x of t, y of t, the product of the time domain signal. Apply the Fourier transformation of that signal, you'll get convolution of frequency domain signals with 1 by 2 pi is a factor. Okay, already we've seen the convolution in time domain. Convolution in time domain saying that z of t is equal to convolution, time domain convolution y of t, the Fourier transformation z of omega is equal to x of omega into y of omega. That's a product here. Time is convolution and time is product, frequency is convolution. And in the Fourier series also, in the Fourier series, time is convolution, frequency is product with a factor of t because it is a periodic signal, t into x of k, y of k. But in the modulation, x of t and the y of t, the Fourier series z of k is equal to x of k with the convolution of y of k. Following my students, the modulation time domain corresponds convolution of spectrums in frequency domain. Convolution of spectrums in frequency domain. Now, to prove this modulation in time domain, modulation in time domain, modulation is nothing but the product here. Okay, combining z of omega is equal to, according to the Fourier transformation equation, z of omega is equal to integral minus infinite to infinite z of t e power minus j omega t d omega. Okay, now we'll explain in the whiteboard. So the modulation in time domain. Modulation in time domain. So what is the statement saying that if x of t, the Fourier transformation x of omega, and y of t, the Fourier transformation y of omega, then modulation in time domain means taking z of t is equal to product x of t and y of t, the time product. Its Fourier transformation is z of omega is equal to, with a factor of 1 by 2 pi x of omega convolution with y of omega. Okay, my dear students, you have to prove that one. Let me go for the proof. For the Fourier transformation definition, saying that z of omega is equal to integral minus infinite to infinite z of t e power minus j omega t dt. Okay, that is equal to integral minus infinite to infinite. What is the z of t? Is a product of signals x of t, y of t, e power minus j omega t dt. Okay, my dear students. And taking the product, the modulation in the time domain. Now, according to the inverse Fourier transformation definition, saying that x of t is equal to 1 by 2 pi integral minus infinite to infinite x of omega into e power j omega t into d omega. Okay, my dear students. So with respect to the omega, now a little bit you have to change here as 1 by 2 pi minus infinite to infinite, changing it as a lambda, x lambda into e power j lambda into t d lambda. Here the omega is a variable and here the lambda is a variable, because whenever if it is substitute the x of t in this equation, here e power minus j omega t and plus e power j omega t. Suppose we'll get cancelled there. E power 0, nothing but the value is 1. We get the value is 1, we can't prove that it is a z of omega is equal to as a convolution function. Okay, so that advice to change the omega as a lambda. Simply it is also the same variable. Substituting in this one, integral minus infinite to infinite. What is x of t? 1 by 2 pi integral minus infinite to infinite x of lambda e power j lambda into t lambda is a total equation for x of t, and the remaining is a y of t there. Y of t e power minus j omega t dt. Okay, now rewrite this function. 1 by 2 pi is a constant. For the first integral, minus infinite to infinite, take the y of t dt. Y of t dt. Another integral minus infinite to infinite, x of tau okay, or otherwise you can take it, this one is directly the x of tau here itself, minus infinite to infinite x of tau d tau is the first integral. For the second integral minus infinite to infinite y of t, here the y of t is there, and take these two exponential fractions e power, both are the same base, take the minus j, omega is here, the omega minus here the lambda is there, minus into minus is a plus, into t dt. Right. So y of t e power minus j omega minus lambda into t dt. See, in this equation, according to the frequency domain, not the frequency shift property, according to the frequency shift property, if the signal is x of t e power minus j omega minus beta into t dt. So x of omega minus beta. We already seen that in the frequency shift property. So instead of x of t, here the y of t. It becomes of z of omega is equal to 1 by 2 pi. The first integral is the integral minus infinite to infinite x of tau d tau, and this total equation is here. This is a total equation, integral minus infinite to infinite y of t e power minus j omega minus lambda into t dt. If it is a omega, it is y of omega. But instead of omega, omega minus lambda. So y of omega minus lambda. We write this expression 1 by 2 pi integral minus infinite to infinite x of lambda y of omega minus lambda into d lambda. See, this is the equation of the convolution. What is a convolution integral? Convolution integral formula. We already seen this formula in the convolution in time domain property. Integral minus infinite to infinite x of tau y of t minus tau beta for convolution of x of t with y of t is equal to. Following my students. What is the formula here? The integral minus infinite to infinite x of tau y of t minus tau beta. Now compare these two equations. Instead of tau, it is a lambda. X of tau, y of t minus tau, d tau. And instead of t, here the omega is there. Omega. So whenever here the t is there, in the left hand side you can observe x of t with the convolution of y of t. But in this equation, tau is lambda and t as omega. Therefore, z of omega is equal to here 1 by 2 pi is there, 1 by 2 pi whole multiplied with what is according to this equation in the left hand side, x of t with the convolution of y of t. Instead of t is here. But here as a t variable, the omega is there. So x of omega with the convolution of y of omega. But students, it is also very important property. Modulation in time domain. Understood? First of all, I take the z of omega is equal to as a Fourier transformation definition. Substitute the z of t according to the given x of t, y of t. From the definition of inverse Fourier transformation, x of t is equal to 1 by 2 pi integral minus infinite to infinite x of omega e power j omega t d omega. Change the variable omega as a lambda here. Substitute this equation as x of t and y of t e power minus j omega t dt. And rewrite this expression as one integral as a lambda and another integral is all the t terms, t, and t. Now, according to the frequency shift property, in this equation we got according to the frequency shift property, integral minus infinite to infinite y of t e power minus j omega minus lambda into t dt can written as y of omega minus lambda. So 1 by 2 pi integral minus infinite to infinite x of lambda y of omega minus lambda d lambda. The convolution integral according to the convolution integral x of t with the convolution y of t is equal to integral minus infinite to infinite x of tau y of t minus tau d tau. Therefore, z of omega is equal to, comparing these two equations, the tau is lambda there and t is omega is there. So x of omega is convolution with the y of omega. Alright, my students. Then you go for here. So the modulation theorem saying same thing. X of t, y of t power minus j omega t d omega. According to the inverse Fourier transformation states that x of t is equal to 1 by 2 pi minus infinite to infinite. The directly taken is a lambda. X of lambda e power j lambda t d lambda. Substitute here and rewrite the expression, the tau and the t terms. Integral minus infinite to infinite y of t e power minus j omega minus lambda into t dt. The frequency domain, not the frequency domain, frequency shift property is saying the y of omega minus lambda. And this equation is the convolution equation, 1 by 2 pi x of omega with the convolution y of omega. Ninth property of the modulation. Ninth property of the Fourier transformation. See, in the Fourier series also the modulation is there. Convolution integral is also there. And the convolution integral, convolution time domain. Until now we discussed about the 9 properties in the Fourier transformation, except integration and the frequency differentiation, the remaining all there in the Fourier series also. Understood, my students? Coming to the duality property. Duality property. The duality property is also not there in the Fourier series. This is the third one. 10 properties we discussed. 3 properties are different, which is not there in the Fourier series properties, and the remaining 7 properties are there in the Fourier series also. The names same: linearity property, time shift property, frequency shift property, scaling property, time differentiation property, and convolution in time domain, modulation in time domain. Now the duality property. Duality. It is also very important property. In some of the examples, we are using this property to solve a simple way. Even the complex problems also, by using this duality property, we can easily simplify that problems. How we can derive this? See the statement of duality property saying that if x of t, the Fourier transform x of omega, then observe here, x of t, the capital letter will get in the left hand side. Actually, the time domain function is always represented with a small letter, and frequency domain function is always represented with the capital letter, my dear students. Duality. X of t, the Fourier transform 2 pi into x of minus omega. Something manipulation will get did to prove the duality property here. See, the inverse Fourier transform is given as x of t is equal to 1 by 2 pi integral minus infinite to infinite, integral minus infinite to infinite, x of omega e power j omega t d omega. So the interchanging of t by omega, as a t is a variable, omega is also variable. Now I am interchanging t as omega, omega as a t, and omega as a t, and the t as omega, so both are e power j omega t only. Omega with the t. Follow my students, interchanging the t by the omega, or omega by the t. The t, x of t, I change as x of omega, 1 by 2 pi and 1 by 2 pi, the integral minus infinite to infinite, x of t, omega as a t here, and e power j omega t, omega is t and the t omega both are the same, d omega and the dt. Following, interchanging. Now it is also interchanging the omega, the same function, nothing is difference. Now interchanging omega by the minus omega, or not to say the interchanging, the replace omega by minus omega. X of omega here, the minus x of minus omega is equal to 1 by 2 pi integral minus infinite to infinite x of t. Here also the omega is there, replace that omega by minus omega. Replace omega by the minus omega, x of minus omega is equal to 1 by 2 pi integral minus infinite to infinite x of t e power minus j omega t dt. Now cross multiply the 2 pi here. 2 pi into x of minus omega is equal to integral minus infinite to infinite x of t e power minus j omega t dt. Now in the right hand side, the above equation is a Fourier transformation of x of t. Fourier transformation of x of t. So the Fourier transformation of x of t, saying that x of omega is equal to integral minus infinite to infinite x of t e power minus j omega t dt. The definition of the Fourier transformation. In this, x of t and x of omega are pairs. X of t is a Fourier transformation of x of omega. Alright. Now, in this equation, C is the same. Instead of x of omega, the 2 pi the x of minus omega, integral minus infinite infinite x of t e power minus j omega t dt. What is the base here? 2 pi x of omega is a Fourier transformation pair with x of t. So x of t is a Fourier transformation pair with 2 pi x of minus omega. It's a duality property. What we did here, taking the inverse Fourier transformation formula and interchange t by omega. Interchange t by omega. This is the same equation, no need here. So repeated. The first you can take the inverse Fourier transformation formula, interchange t by omega, x of omega, 1 by 2 omega, integral minus infinite infinite x of t e power j omega t dt. In this equation, replace, here also you can take this one. Replace omega by minus omega. We get x of, in this equation, x of minus omega 1 by 2 pi integral minus infinite infinite x of t e power minus j omega t dt. And the 2 pi can cross multiply here, 2 pi into x of minus omega integral minus infinite infinite x of t e power minus j omega t dt. So now these two are the Fourier transformation pairs. Okay, so x of t in the time domain, you can take it in the left hand side, Fourier transformation pair with 2 pi into x of minus omega. Follow my students. Next, coming to the another property, symmetry property. And this symmetry property also we have in the Fourier series. It's x of t is a real, and x of t is a real and even, and x of t is a real and imaginary, like that. But here the symmetry property, if x of t is a real signal, if x of t is a real signal, and x of omega as a real function xr of omega plus j into xi of omega, imaginary function. Real term and the imaginary term as x of omega. Then we can prove that the even part of the time domain signal is a Fourier transformation pair of xr of omega. And odd part of the time domain signal xo of t is a Fourier transformation pair of j into xi of omega. Okay, and here the xc of t and xo of t are even and odd parts of x of t. Even and odd parts of x of t. Following my students. So first of all, I am taking to prove this symmetry property. X of t is a Fourier transformation of a real function and the imaginary function, because you see we have the x of t is a Fourier transformation of x of omega. What is the x of omega is given here? X of omega is equal to xr of omega and j into xi of omega. So x of t is a Fourier transformation of xr of omega plus j into xi of omega. This is a given here. Let x of t be real signal and x of omega is equal to real part and the imaginary part in the frequency domain. So x of t is equal to Fourier transformation pair of xr of omega plus j into xi of omega. Now since x of t is a real, x of minus t is also will get it as a positive plus x of minus t. I'm taking here the x of t is a real, x of minus t is a Fourier transformation pair of it is x of omega is now it is x star of omega. It's a conjugate. What is a conjugate saying? X r of omega plus this now becomes of minus j x I of omega because it is a complex function. Since x of t is a real, x of minus t is a Fourier transformation pair of x star of omega, and this function is x of omega only. Whenever if I am taking the negative values, x star of omega will get x star of omega. We already seen in the time reversal property. Okay. What is that x star? When we have the two terms as a real and imaginary, real is a positive and imaginary changes as a positive to negative and negative to the positive for the conjugate. We got the two functions. When x of t having the two terms, x of minus t is also having the two terms with the sign is a difference for the imaginary functions. The even part is given as xc of t is equal to, how we got this function? Let x of t is equal to it having the even and odd parts, xc of t plus xo of t, and x of minus t is equal to x e of minus t. So I'm replacing the t as minus t and xo of minus t. For even functions, for negative values also you get the positive value only. The even function is nothing but cos function. Even is cos x is equal to cos of minus x. Okay. Odd function means sin x is odd function. Is the sign of minus x is equal to minus sin x. Okay, is equal to the minus sin x minus 2 for odd function. So even function and odd function we already know. For negative values also it is a positive value. For odd function is a minus of x of xo of t. I'm not taking it as a minus here. There is already odd function. Okay. Now I'm adding these two functions, x of t plus x of minus t is equal to, what is x of t? Xe of t plus xo of t. What is x of minus t? Xe of t minus xo of t. When I am adding these two functions, xo of t and xo of t get cancelled and 2xe of t. So what is the even part? Xe of t is equal to x of t plus x of minus t divided by the 2. The even part. That only here saying xe of t is equal to 1 by 2 x of t plus x of minus t. Okay. Now applying the xu of t is a Fourier transformation. Fourier transformation. X of t as x of t is x of omega, and x of minus t is x star of omega. X of t, the Fourier transformation. For this, I am applying the Fourier transformation here. For x of t, the Fourier transformation is x of omega. For x of minus t, the Fourier transformation is x star of omega. What is x of omega? X star of omega plus j xi of omega, and x star of omega is x star of omega minus j xi of omega. Now you can get cancelled these are plus and minus. 2 xr of omega, here 1 by 2 is there, 2 xr of omega. It is something wrong here. Actually, it is 2 xr of omega, and 2 to get cancelled. Xe of t is a Fourier transformation pair of xr of omega. xr of omega. Understood? So that is the first one. Then you have to prove xe of t is a Fourier transformation of xr of omega. And what is the second one? You have to prove the xo of t is a Fourier transformation of j into xi of omega. How we got the odd part? In these two equations you can add, you get the 2 xe of t. But when subtraction, x of t minus x of minus t is equal to, and these two equations you can subtract xe of t plus xo of t minus xe of t plus xo of t. So even terms get cancelled, you get the odd terms, odd 2 into xo of t. So what is the xo of t here? Xo of t is equal to x of t minus x of minus t whole divided by the 2. That only here we'll get xo of t is equal to 1 by 2 x of t minus x of minus t. What is the, when I'm taking the Fourier transformation here, the Fourier transformation of x of t is xr of omega plus jxi of omega, and x star of omega is a xr of omega minus jxi of omega, and before that it is a minus xr of omega plus jxi of omega. These are plus and these are minus. The real term get cancelled, and we have only the imaginary term, that is a 2 into xi of omega. 2 into xi of omega. 2 to get cancelled, and we have j term is there. J into xi of omega. 1 by 2, 2 into j xi of omega. 2 to get cancelled, j xi of omega will get. So x naught of t is a Fourier transformation pair of j into xi of omega. J into xi of omega. The symmetry property in Fourier transformation. Understood, my dear students? Coming to the next one, Participles Theorem. And this property is also in the Fourier series. We already seen the Participles Theorem. It is also called as Rayleigh Theorem. We heard this one. EC students, everybody know that Rayleigh's will get in the PTSP or RVSP. Now we are saying that it is RVSP, random variable and stochastic process. It is a name we already heard, the Rayleigh's theorem, binomials theorem, Rayleigh's theorem. Okay. So the Participles theorem for the Fourier transformation, call it as the Rayleigh's theorem. What is the statement here? If x of t is a Fourier transformation of x of omega, then the energy signal integral minus infinite to infinite squared magnitude of x of t dt is equal to 1 by 2 pi the squared magnitude of the frequency domain x of omega d omega, and it is also equal to the squared magnitude of x of f into df. So you can prove that. What is the meaning here? The energy of a signal can be obtained by interchanging its energy spectrum. Interchanging. If your x of t is here, the frequency domain function is x of omega. When in the angular frequency, the normal frequency is also x of omega. The interchanging its energy spectrum. Energy of a signal can be obtained by interchanging its energy spectrum. So the proof here. First of all, you can take the energy E is equal to integral minus infinity to infinity the squared magnitude of x of t. We know the squared magnitude of x of t is equal to x of t x star of t. We already know this equation. We prove the Participles Theorem in the Fourier series. So energy E is equal to minus infinity to infinity the squared magnitude of x of t dt can be written as x of t x star of t, the conjugate function, into dt. According to the inverse Fourier transformation, x of t is equal to 1 by 2 pi integral minus infinity to infinity x of omega e power plus j omega t d omega. J omega t d omega. Listen carefully, my dear students. So now I am taking the conjugate on both sides. It becomes of x star of t is equal to 1 by 2 pi integral minus infinity to infinity. So I am taking the star here. For this function also, x star of omega, the conjugate of the frequency domain function, and the plus exponential value becomes of minus j omega t dt. For the dt, it is a d omega. Don't write this a star here with respect to or applying the omega only. Only there is a changes occurs for the imaginary terms because it is a complex d omega. Now replace this x star of omega in this energy equation. So energy E is equal to integral minus infinity to infinity x of t, and replace the x star of t with this equation. What is x star of t? 1 by 2 pi integral minus infinity to infinity x star of omega e power minus j omega t d omega as of x star of omega, x star of t and dt. Okay, so in this equation, now rearrange these expressions of the two integrals. 1 by 2 pi integral minus infinity to infinity x star of omega d omega. The omega terms is one integral, and the remaining two integrals, t integrals, integral minus infinity to infinity x of t e power minus j omega t, all the t terms keep it in the another integral. See, this is the expression of According to the Fourier transformation equation, integral minus infinite to infinite x of t e power minus j omega t dt as x of omega 1. So 1 by 2 pi integral minus infinite to infinite x star of omega d omega, and this function is x of omega. Now you can see x star of omega and x of omega. As the squared magnitude of x of t is x of t, x star of t, and now it is also 1 by 2 pi integral minus infinite to infinite x of omega magnitude square d omega. Okay, since x of omega, the squared magnitude of x of omega is equal to x of omega into x star of omega. Follow my students. This is the first equation. Energy, we take integral minus infinite to infinite squared magnitude of x of t dt is equal to 1 by 2 pi integral minus infinite to infinite squared magnitude of x of omega d omega. Okay, and what is the last one? See, only we know the omega is equal to 2 pi f. What is the d omega? Apply the derivative on both sides at 2 pi into df. 2 pi into df. So replace here the omega is equal to 2 pi f, and shortcut notation x of omega is equal to x of 2 pi f, the shortcut notation x of f only. Okay, this becomes of 1 by 2 pi integral minus infinite to infinite the squared magnitude of f into what is the d omega? We got 2 pi into df. 2 pi into df. Okay, my dear friends, this 2 pi and 2 pi get cancelled. The last term, not the last term, it is equal to the integral minus infinite to infinite the squared magnitude of x of f into df. Understood? Take this as a screenshot, my dear students, because it is not there in the printed wise. The Participles Theorem. So take the screenshot and put it. Okay, everybody can take the Participles Theorem. These are the 12 properties. These are the 12 properties in the Fourier transformation, my dear students. Okay, so what are the 12 properties? Once again, I'll recall all the properties. The first property, linearity property. Linearity property. And second one is time shift property. Time shift. And third one is frequency shift property. Frequency shift property for the Fourier transformation also. And fourth one is time scaling property. Time scaling property. And fifth one, frequency differentiation property. Frequency differentiation. And sixth one is time differentiation property. Time differentiation property. And seventh one, convolution property. Convolution. And eighth one is integration property. Integration property. And ninth one, modulation property. Modulation property. And 10th one, duality property. Duality property. And 11th one, symmetry property. Symmetry property. And the last 12th one is a Participles theorem. Participles theorem, also call it as Rayleigh's theorem. So these are the 12 properties there in the Fourier transformation. Fourier transformation. See, in the Fourier series also we have the linearity property, time shift property, frequency shift property, scaling property, time differentiation property, convolution property, modulation property, and symmetry parsecs. How many? 1, 2, 3, 4, 5, 6, 7, 8, and 9 properties are there in the Fourier series. With the same name, 9 properties in the Fourier series. Here in the Fourier transformation, there is a 12 properties. What is the remaining here? New one is a frequency differentiation property and integration property and a duality property. Duality property. So 10, 11, and the 12. Frequency differentiation, integration, and duality property. So how many properties we learned till now? Both the Fourier series and the Fourier transformation, 9 plus 12 properties. We thorough these 12 plus 9 properties, totally it's 21 properties. 21 properties. It is easy to solve the examples what they given in the Fourier series or what they given in the Fourier transformation. In the simple way, by using these properties, we can solve easily. If they ask in the problems, following. So please we practice the Fourier series and the Fourier transformation 2 or 3 times. It will be understood. And also you can see the Fourier series and the Fourier transformation. Take it as an assignment and write the Fourier series 9 properties and the Fourier transformation and the 12 properties, my dear students. As these 21 properties as a take the assignment. Okay, write all of you by taking off A4 sheet papers and write the assignment. Understood? All the third year and the second year students, third year triple E and second year ECA and ECP students. 21 properties, 9 properties in the Fourier series and 12 properties in the Fourier transform. The next one, come to the examples of the Fourier transform. We already did the some of the examples in the for the Fourier series, because the Fourier series analysis are used to analyze the periodic signals, but the Fourier transformation can also be analyzed for the non-periodic signals. Non-periodic means it is not repeated with the particular interval of the time. Periodic signal means it is repeated with the particular interval of the time. Okay. See the first example of the Fourier transformation here. First example of the Fourier transformation. Find the Fourier transformation of the decaying exponentially. Decaying exponentially shown in the figure. The same example we did for the Fourier series also. It is also the decaying exponential signal. but it is repeated with a interval of 0 to 0.5. 0 to 0.5. The t is 0.5, the time period, and it is repeated for every 0.5, the exponentially decaying function. But now we are finding out the Fourier transformation of the decaying exponential function. Okay. The given x of t is equal to e power minus at. A is a variable here. E power minus at. Why I am taking the mu of t, I will explain here. Normally, to show the time delays in the function and sign of time, use the unit step function mu of t is made. The value of unit step function is always unity. Where it is a unity, my dear students? For t is greater than or equal to 0. For t is greater than or equal to 0. But less than the 0, its value is a 0 here. Okay, for negative real axis, all the values is a 0. For positive real axis only, the unit step function is unity. So for every given function, you can multiply with the step function. But it is not in the Fourier series, my dear students, because the Fourier series is repeated for every interval of 0.5 or every interval of the t, means in the negative real axis also it is repeated. The negative real axis also repeated. But here, because of it's a Fourier transformation, we are finding for the decaying exponential functions. The given signal x of t, the e power minus at is multiplied with the mu of t, since the mu of t is equal to 1 for 0 to infinite values of the t. 0 to infinite values of the t. According to the definition of the Fourier transformation, here you take the normal frequency. You can take the x of omega also, my dear students. Nothing will wrong. X of omega is equal to integral minus infinite to infinite x of t e power minus j 2 pi f into t dt. Otherwise, x of omega is equal to integral minus infinite to infinite x of t e power minus j omega t dt. Omega is nothing but 2 pi f. Okay, my dear students. So x of f is equal to, substitute the x of t as a given function e power minus at mu of t. E power minus at mu of t, e power minus j 2 pi f into t dt. And now I change the limitations here 0 to infinite because of the step function is valid only for positive real axis. For negative real axis, the values are the zeros. So I change the limitation from minus infinite to infinite as 0 to infinite. Since the mu of t is a 1 from 0 to infinite. So e power, these two bases are equal. So add the powers here, e power minus at minus j 2 pi f into t. Take the common of minus a 2 pi f into t dt. We know the integral of exponential value. The integral of exponential, e power minus jx is there. E power minus jx by the minus j. Here e power minus jx, what is a t with respect to we are applying? The t coefficient is minus a plus j 2 pi f. The upper limit is infinite and the lower limit is a 0. When you substitute the upper limit as a t is equal to infinite, anything power infinite is a value is a 0, my dear students. Anything power infinite, the value is 0. E power infinite is a 0. It is a plus or minus. E power, it is a plus or minus 0, the value is a 1. Okay, remember this one. Anything power infinite is a 0. Anything power 0 is a 1. So the upper limit when I am substituting with the t value is infinite, that is a 0 minus e power 0, the value is a 1. And here the minus and the minus becomes of the plus 1 by a plus j into 2 pi f. What is a 2 pi f? Nothing but omega also. So x of omega is equal to, when I take the omega, 1 by a plus j omega as of angular frequency. What is the normal frequency? X of f is equal to a plus j 2 pi f. Replace the omega as a 2 pi f. For decaying exponential pulse e power minus at mu of t, the Fourier transformation is the decaying exponential pulse e power minus at mu of t is 1 by a plus j 2 pi f, or 1 by a plus j omega in angular frequency and the normal frequency. Okay, my dear students. To calculate the magnitude and the phase spectrum, so what they're asking here, it is a determine or find the Fourier transform of decaying exponentially as shown in the figure. Okay, it's completed up to this. The Fourier transformation of the e power minus at mu of t is 1 by a plus j omega. But to find out the phase and the magnitude of this equation, x of f is equal to a of f plus j into b of f. A of f is a real part of x of f and b of f is imaginary part of x of f. How we can find out this magnitude? Square root of a of f square plus b of f square. And the phase spectrum is inverse, tan inverse of b of f whole divided by a of f. Okay, you know already how you can find the magnitude and the phase for the given rectangular form. X plus iy, magnitude is under root of x square plus y square, and phase is tan inverse y by x. Tan inverse y by x. But here the phase angle is, see my dear students, the phase angle is different. When the first quadrant and in the second quadrant and in the third quadrant and fourth quadrant. Why? In the first quadrant x plus iy, because x value is a positive here and the y value is a positive value. And this is the imaginary axis and this is the real axis. Okay, in the first quadrant x plus iy, but in the second quadrant minus x plus iy. Minus x plus iy. For this, magnitude is the same, but angle is a difference, my dear students. Okay, angle is a difference. And here, for the third quadrant, minus x and minus y. So minus x minus iy. And for this also the magnitude is the same. For this also the magnitude is the same, my dear students. And here, x minus iy. X minus iy, and for this also the magnitude is the same, x square plus y square under root of all the quadrants. Magnitude is same, but angle is a difference, my dear students. What is the angle here? Tan inverse, when both are positive values, tan inverse y by x is a plus tan inverse. Coming to the fourth quadrant, it is not the angle is a plus, minus tan inverse y by x. Whenever if we can take as x minus iy, x minus iy minus y by x. And coming to here, minus x plus iy and minus x minus iy means we can add the 180 degrees and we can subtract the minus 180 degrees. Following, my dear students. For the same, tan inverse y by x, for tan inverse y by x. And time we can add the plus 180 degrees for the same function and minus 180 degrees. Here it is a minus, and for this one we can add 180 degrees. Alright, here 180 degrees plus tan inverse y by x, and here minus 180 degrees with the 180 degrees minus tan inverse y by x. That is a very, very important. Third year triple A, they know because they completed the control systems subject. In the border plots, they will get that one. But the second year students, you have to know when it is a minus and when it is a plus value, and when it is added off 180 degrees for this one, and when we can subtract the 180 degrees that one. Following my dear students. Okay. So the decaying exponential pulse e power minus at mu of t is 1 by a plus j 2 pi f. Now consider here the x of f is a 1 by a plus j 2 pi f, rationalized with a minus j 2 pi f, a minus j 2 pi f, and denominator we have a plus b into a minus b, a square plus b square, and the real part is a by a square plus b square plus j imaginary part minus 2 pi of a square plus 2 pi of whole square. Find the magnitude, real term square and plus imaginary term square, and find the phase, imaginary term by real term. So both the denominator same, minus 2 pi f by a. Here the minus means tan inverse of minus theta is a minus tan theta. Minus tan theta. So minus tan inverse 2 pi f. Alright. Then substitute the k values or the t values here. F values. So take the f values, substitute the f. Let us say the f is equal to 0. F is equal to 0 means the term is a 0 here. 1 by a square. 1 by a square under root by 1 by a. 1 by a. And this value is a 1. And slowly it is a decreases. And for the negative value, slowly it is a decreases. For positive 1 and positive 1, both are the same. Minus 2 and minus 2 is also the same. Minus 3 and minus 3 is also the same. The magnitude spectrum. And phase spectrum is varies between 90 degrees and the minus 90 degrees. How? See, if I am taking the tan inverse f is equal to 0. F is equal to 0 means tan inverse 0. Tan inverse 0. 0 is equal to 0 now here. So on it is increases and up to here. At the infinite there is a minus infinite is there. Minus infinite. Tan inverse infinite. Here it is a f we can take is an infinite value. Tan inverse of infinite. Nothing but pi by 2. Tan inverse of minus infinite. Nothing but minus pi by 2. Okay. Minus pi by 2. And the positive value infinite, that is a tan inverse minus infinite minus pi by 2. And tan inverse minus infinite means minus of minus is a plus. It becomes of pi by 2. Understood, my dear students? So it varies from 0 to pi by 2 to the pi by 2. So I think it is a little bit confusion. Some of the students tan inverse 2 pi f by a minus is also there. If I am taking the f is equal to 0, it becomes of tan inverse minus 0. Minus 0 or the plus 0, whatever it is, a 0 on. Tan inverse 0 is a 0. 0 degrees here. See at the 0, it is a 0 degrees on. Now if I am taking the f is equal to infinite, f is equal to infinite means tan inverse of minus infinite. Here it is a minus already there. Tan inverse minus infinite minus tan inverse infinite. This becomes of minus pi by 2. For positive values, here let us be infinite is there. Angle is minus pi by 2. So I am taking the f is equal to minus infinite. Tan inverse minus of minus infinite. it becomes of tan inverse infinite only. That value is a pi by 2. So for the minus infinite, the angle is pi by 2. The phase spectrum and magnitude spectrum. Understood, my dear students? So very important it is. Okay. So any doubt up to this, the properties and one of the example. Please rise. Okay. Thank you. Thank you, one and all.